Asteroid impacts have played a major role in shaping Earth's geological and biological history. One of the most dramatic examples is the mass extinction event 66 million years ago, which wiped out nearly 76% of all species on Earth. Although large asteroid impacts are extremely rare, their consequences can be catastrophic. In contrast, smaller impacts occur much more frequently, but they typically cause limited or no damage. Every year, Earth accumulates approximately 15,000 tons of meteoric material. On a daily basis, nearly 25 million meteors enter the atmosphere. Most of them are microscopic and burn up completely. The largest incoming objects on a typical day are around 40 centimeters in diameter, but only a very small number survive passage through the atmosphere to become meteorites. Occasionally, bright fireballs streak across the sky, signaling larger objects burning up at high speed. Asteroids around 100 meters in size are estimated to impact Earth roughly once every 2,000 years, creating significant regional destruction. Meanwhile, extremely large asteroids, greater than 10 kilometers, are capable of triggering global-scale catastrophes, though these occur only once every several million years. Fortunately, the larger an asteroid is, the easier it is to detect. NASA is confident that it has identified nearly all near-Earth objects larger than 10 kilometers. However, smaller asteroids still pose potential threats at local or regional levels. A recent reminder was the 2013 Chelyabinsk explosion in Russia, where a 20-meter asteroid detonated in the atmosphere, injuring about 1,500 people and damaging thousands of buildings. These realities highlight the critical need for robust detection systems and effective planetary defense strategies to mitigate potential asteroid hazards. NASA's Double Asteroid Redirection Test, commonly known as the DART mission, was the world's first attempt to alter the trajectory of an asteroid using a kinetic impact. This groundbreaking mission was developed through a collaboration between NASA, the Johns Hopkins Applied Physics Laboratory, and several international partners, including Italy, Japan, and the European Space Agency. Before DART, various asteroid deflection concepts had been proposed. These included the gravity tractor method, where a grafter would gradually shift an asteroid's path using gravitational pull, the use of nuclear explosions, which could potentially shatter an asteroid into hazardous fragments, and reflective mirror arrays designed to induce outgassing on comet-like bodies. Among these ideas, DART chose the simplest and most controlled approach, a direct kinetic impact designed to give the asteroid a slight but measurable push. The target was Dimorphos, a 160-meter-wide moonlet orbiting a larger asteroid named Didymos, which measures roughly 780 meters across. Dimorphos circles Didymos at a distance of about 1 kilometer, completing an orbit every 11.9 hours. The larger system itself orbits the Sun every 2.1 years. In October 2022, the system passed within 10.6 million kilometers of Earth, making it a perfect candidate for testing without posing any risk. The DART spacecraft weighed approximately 610 kilograms, about the size of a household refrigerator. It carried a single high-resolution camera called Draco and operated using autonomous navigation due to the communication delay between Earth and the spacecraft. A small companion satellite, the 14-kilogram LICIACube, was deployed 15 days before impact to capture close-up images of the collision and the resulting debris plume. In the final moments of the mission, DART captured images until just 2 seconds before impact. The collision delivered around 19 gigajoules of energy, roughly equivalent to 5 tons of TNT, and is believed to have produced a crater up to 150 meters wide. The results exceeded all expectations. DART successfully shortened Dimorphos' orbital period by 32 minutes, far surpassing NASA's minimum success criteria of 73 seconds. The orbit changed from nearly circular to slightly more elliptical, and the asteroid's shape and rotation were significantly altered. Observations from telescopes on Earth, along with radar measurements and images from LICIACube, confirmed the effectiveness of the impact and revealed complex ejecta patterns. To further study the aftermath, the European Space Agency launched the Hera mission in October 2024. Hera is expected to arrive in 2026 and will conduct a detailed examination of the impact site, internal structure, and long-term changes in the system. Looking ahead, missions such as NASA's NEO Surveyor, planned for launch in 2028, aim to detect 90% of potentially hazardous asteroids larger than 140 meters, including dark asteroids that are difficult to see with ground-based telescopes. In conclusion, the DART mission marked a historic milestone in planetary defense. It demonstrated that kinetic impact is not only feasible, but also highly effective, representing a crucial early step towards protecting Earth from future asteroid hazards.
The DART mission was not just a demonstration of force. It was a precise scientific experiment designed to measure how a kinetic impact transfers momentum to an asteroid. Behind the simplicity of hitting a rock in space, the mission combined advanced engineering, autonomous navigation, orbital dynamics, and impact physics at an unprecedented scale. At its core was DART's guidance system, known as SmartNav, an onboard autonomous software capable of identifying the target asteroid, tracking it in real time, and adjusting the spacecraft's trajectory without human intervention. This was essential because, at the time of impact, the communication delay between Earth and the spacecraft was more than 38 seconds. By the final minutes, DART was fully on its own, making rapid course corrections multiple times per second to ensure a direct collision. As the spacecraft approached Dimorphos, Draco, the onboard high-resolution camera, served a dual purpose: navigation and science. In the last 4 hours of the mission, Draco began sending detailed images, revealing Dimorphos's shape, surface texture, and boulder distribution. Each frame allowed engineers to refine the path until the final, perfectly centered, high-speed impact. When DART struck Dimorphos at 22,530 kilometers per hour, the effect was far greater than the spacecraft's mass alone would have predicted. This phenomenon, known as momentum enhancement, was caused by the massive plume of ejecta thrown from the asteroid's surface. The recoil created by this debris acted like a booster thrust, amplifying the impact and increasing the orbital change far beyond initial estimates. Scientists estimate that the momentum transfer efficiency may have been anywhere from 2 to 4 times higher than the spacecraft's direct kinetic input. This result was a major breakthrough. It revealed that rubble pile asteroids, those composed of loosely bound rock fragments, respond very differently to impacts compared to solid monolithic bodies. Analyzing the shape and evolution of the ejecta plume helped researchers understand the asteroid's internal structure. The long, comet-like tail, extending thousands of kilometers into space, indicated that Dimorphos consisted of weakly bound material, easily displaced upon collision. This knowledge is critical for future planetary defense strategies because different asteroid types require different deflection methods. DART also provided valuable insights into binary asteroid systems. These systems are more common than previously believed, and understanding their dynamics is essential for predicting long-term orbital evolution after deflection attempts. The change in Dimorphos's orbit from nearly circular to more elliptical will allow scientists to test how small perturbations accumulate over years and decades. Another major legacy of the mission is its contribution to global collaboration in planetary defense. Telescopes around the world, from NASA's Goldstone radar to the Hubble and James Webb telescopes, coordinated observations in real time, making DART the first test of an international asteroid impact monitoring network. This network will be essential in responding to any real threat in the future. The DART mission proved more than its engineering goals. It demonstrated that humanity is not powerless against asteroid threats. For the first time, we altered the motion of a celestial object in a controlled, measurable way. It marked a turning point in space science, transforming planetary defense from theory into a proven capability. As future missions build on this success, DART will be remembered as the technological foundation that made active protection of Earth not just possible, but practical.